So we're going to be using a tool called Solana Playground, which lets us make Solana programs or smart contracts directly in our web browser without installing anything on our local machine. So open beta.solpg.io, click Create a New Project, give your project a name. I'm going to call this project Favorites because it's going to save our favorite things to the blockchain. And we'll pick the anchor option and click Create. There's a file made for you, but let's actually delete everything inside that file, that librs file. We're going to make everything from scratch ourselves. So the first thing you'll see in pretty much any anchor program is importing what's called the anchor prelude, which is the thing you'll see at the top of almost any file and allows us to access everything from anchor just by typing its name rather than typing out the full path to it. So use anchor lang prelude star. That pulls in all of our prelude into the current scope. The double colon is just Rust's separator for namespaces. Other languages would use a dot for the same thing. A program has a program ID, also called an address. I'm going to set up a program address for our smart contract. In Solana Playground, we don't actually need to fill this in. It will be done for us when we deploy our program. Also, just for neatness, I'm going to make a little constant here. And I'm going to call it anchor discriminator size. The anchor discriminator is something that's written to every account on the blockchain by an anchor program that just specifies the type of account it is. And that's used by Anchor for some of its checks. So that is a usize, and the value is just 8. So when we save things to the blockchain, we'll need 8 bytes plus the size of whatever we're saving. You'll see that later on. Now, the great thing about Anchor is that we can take a regular Rust program and with a particular macro, turn it into an Anchor program. So here is just a regular Rust module. Pub mod favorites, and it's going to use all those good things we just imported a moment ago, and it has a function. So pub function set favorites, which is going to return nothing. Oops, return nothing. And here is its body. So this is just a regular Rust module. It's called favorites. It has some functions inside. In this case, just one function, set favorites. But the great thing about Anchor is that if we do this macro program, suddenly that favorites Rust module becomes a full Solana program or smart contract. This is the power of Anchor. It saves you from having to do boring things. And also applies a bunch of sensible safe defaults. So set favorites, that function, is now a Solana instruction handler. It will take instructions that are provided by clients and run them and then save the results to the blockchain. So let's think about what we're actually going to save to the blockchain. We're going to save people's favorite things. So that's going to be a struct called favorites. And inside, we're going to save people's favorite number, which will be a 64-bit or 8-byte number. And we will have a favorite color, which will just be a string. And we'll have a list of hobbies, which will be a vector of strings. So pub hobbies vector, it's a little bit like an array of strings. Now, because we're going to save this to an account, we will also put the account macro on it. And to let Anchor know how big favorites is, we're also going to put this derive init space. That gives us all of our instances of favorites the init space attribute, which is the total space used by all the items inside. We'll also need to specify the size of each individual item to get that. Obviously, strings could be any size at all. So we'll need to specify a max length. That's max len, say 50 bytes, and I'll copy that for hobbies. Hobbies is nested because we have a vector of a certain amount of items and then strings which have a certain size. So for hobbies, we'll say 5 and 50 for the vector and the string, respectively. When people call our set favorites function, they're going to need to provide a list of accounts that they're going to modify on the blockchain. One of the things that makes Solana great is that if there's a bunch of people over here who are running a transaction involving their accounts, and there's a bunch of other people over here running a different transaction involving their accounts, those transactions don't block each other. There's no overlap in the accounts evolved. So Solana can process them at the same time without waiting for the other one to be finished. So we'll make a struct to store this information, and we need to come up with a good name for it. Now, this is the struct of accounts for our set favorites instruction handler. So the tradition is to call this struct of accounts the same thing as our set favorites instruction handler, just in title case. Structs in Rust have title case, and the convention is to name the struct the same thing as the function itself, just in title case. We could call this set favorites accounts, but it's good to get along with other people, and this is the convention. So pub user, we're going to need people to supply an account that we call the user, and that's going to need to be a signer. You'll see me doing this info stuff here. All that is saying these items will live for the lifetime of a Solana account info object. This is just Rust having rules about how long things should be kept in memory. This isn't a Rust course, so I'm not going to go into lifetimes fully, but we'll throw some links in the course description so you can learn a little bit more about lifetimes if you want to. So we're going to specify some options for this account. We're going to say that the signer is mutable. Why? Because the person that signs the instruction to set favorites is going to pay to create their favorites account on the blockchain. We're going to pay to store that information. Also, we'll need the person running set favorites to specify the favorites account that they want to write to. It doesn't mean that we'll let them write to this account. We just need them to specify the account. So we'll call that pub favorites. And the type is it's an account that goes for the lifetime of info, and it is an account, which is an account of this favorites struct that we made earlier. We're going to add a few anchor account options as well to favorites. The first thing we're going to do is specify init if needed. Init if needed says make the favorites account if it doesn't already exist. We'll specify who pays to create the account, which, as we said before, will be the user, this person here. And that means the user is the person who signed the transaction. So the person who signed the transaction will be the person who pays to create the favorites account. We're going to tell Solana how much space this account needs. So every account in Anchor has 8 bytes, or the Anchor discriminator size, using that constant we made earlier, plus whatever the size for this struct. So when we made our favorite struct, which specified what favorites look like, their types and the different keys that we need, we said derive init space. That gave us this great init space trait, which we are using to calculate the size we will need for a favorites account. In other words, a favorites account is just an account that has an anchor discriminator and stores favorites. We'll need to have some seeds. Now, the seeds are what's used to give this account an address on the blockchain. This is a program-derived address. Unlike regular user accounts, this isn't a public key. The address for this is actually made based on some seeds that we provide. So if ever you've used a key value store, this is a really similar concept. The keys, in this case, are whatever we have as our seeds. And I'm going to use, in this case, the text favorites as bytes and just the user's own key as well. This means that if I'm storing my favorites, I will store that under the address made from favorites as bytes and my own public key. And if I'm storing your favorites, I will store that under an address made from favorites as bytes and your public key. So what we're doing here is storing information under different accounts that are found based on the inputs we give, and the inputs we give are based on the users. Finally, we'll also specify the bump, which is just used to calculate those seeds. We have pub favorites, and it's an account of type favorites. That looks good. The last thing we'll need to, the last account we'll need people to specify is just the system program. The system program is used for so many things in Solana. If it's not the system program, it's the token program. So that will be a program. It lasts for the lifetime of info, and it is a program of type system. That looks good. So at this point, we have our favorites struct, which is what we're going to write into the blockchain for every user. And we have our set favorites list of accounts that people need to provide, which is also a struct. Let's go and fill in our set favorites function, which is our actual instruction handler, the thing that people are going to call from the instructions in their Solana transactions. We can do, let's do a little greeting message. Solana has this message macro that's built into it, or Anchor actually has this message macro that's built into it. We can do things like greetings from, and we can say context .pro. So message is kind of like console log or print line. It just writes things out to the Solana log file. If you use Solana Explorer, you'll actually be able to see these messages when someone has a transaction that makes a call to this instruction handler. Let's also make a little variable just to show the user's public key, the person who's calling our instruction handler. User public key equals context.accounts.user.key. That's good. Let's add another log message that just logs out the options that people have provided. User Now I just realized that we needed to provide some arguments to set favorites, and we haven't done that yet. So let's do that now. Context. The first argument to our set favorites instruction handler will be a context, which is a context of set favorites. In other words, the set favorites accounts that we made earlier. And I will spell favorites using American English. So I'm consistent. We'll also ask people for all the options they want to save. So that's the number, that U64, the color, which is a string, and hobbies, which is a vector of strings. Save and let Solana Playground do its formatting, and that looks good. So yeah, our set favorites has a context, a number, a color, and hobbies. And you can see that we can access information about like what program we're part of or all the accounts that people have specified through that context parameter. So back to our message, we have user public key, and we're going to log that their favorite color is, or their favorite number favorite color is color, and their hobbies are hobbies. And just because hobbies is a vector of strings, we're going to add a colon and a question mark so it expands the items inside that vector of strings. The last thing we need to do inside our set favorites function is go and actually write the information into the favorites account provided. So that is context.accounts.favorites And if we do a set inner, we can write information into that account. And the information we write will be an instance of the favorites struct with the number, the color, and the hobbies that have been provided. That looks good. Finally, we will return just with OK and nothing, that empty brackets. And we don't need a semicolon on that last line. We omit the semicolon and Rust returns the actual OK response. This is how Solana instruction handlers work. They write information to the blockchain rather than returning it. So that's our completed anchor program. We import the prelude. We set up the ID or program address. I like to make an anchor discriminator size rather than adding 8 later on, because we know that's how much space that every anchor account needs at minimum. We have a Rust module that has functions inside, and we apply this Solana program macro that turns that Rust module into an anchor program. And then inside that module, each function becomes an anchor instruction handler. Each instruction handler has a context, which is all the accounts that the people calling that instruction have provided, plus any other arguments for the instruction. We're going to log a couple of things, and then we're going to save the information somebody has provided to the favorites account. We return OK, just to let calling programs know that this instruction was completed successfully. If all the instructions in a transaction complete, then the transaction is considered complete and everything is written out to the blockchain. If anything fails, then nothing changes. And we have 2 structs. We have our favorite struct, which defines what we want to write out to the blockchain. In this case, a number, a color, and hobbies. And also we're going to add this great init space macro so we can easily calculate how much space it will take to store that. And finally, we have our accounts struct, which I actually realized we need to add derive accounts to the top of so that Anchor knows this is our account struct. And that specifies the accounts that people need to provide along with the instruction. So in this case, it's just the user, the favorites account, and the system program. One of the things that is great about this program is that it already ensures that the person that is signing the program has to be writing to their own favorites account. And we'll test this in a sec, but I want to show you the logic here. In our account struct, we say we have an account called the user, who is whoever signed the transaction. And in our favorites, we say that favorites accounts, the seeds that are used to find its address, are made from favorites and that user's key. So if Alice signs this transaction and tries to write to Bob's account, it won't actually work because the address of the favorites account won't actually match her user account. We'll see this in a second, but it's a good example of one of the things that Anchor provides for us out of the box in terms of smart, safe defaults. Cool, so that looks good. I am going to build this program. So I'm going to slide this little doohickey at the bottom up. So let's click the build button and build our program. We might have some errors, we'll find out. Yep, and we do. It looks like I made a typo because I'm not very good at talking and typing at the same time. I meant to return a result. Instead, I wrote the word return. So let's go and fix that. That returns a result of nothing. There we go. And let's build again. There's another error. Let's go have a look at the first one. I can see that's really obvious. It says on line 44, we have derive accounts, and that should actually be a capital. So if we build once more, you can see the syntax highlighting actually makes that look a little bit better as well for the accounts. You can see that completes successfully. That's great. Now, we will need to deploy. When we go and deploy, Anchor will actually go and make a key pair for us. We can save this if we want to. I'm not going to use this again, so I'm not going to, but maybe you should save the key pair. And it says we don't have enough SOL to complete the deployment. I'm not going to request an airdrop. Instead, I am actually going to use the Solana faucet, which has some more features to get airdrops than the inbuilt Solana Playground airdrop tool. An airdrop, by the way, is just a way of getting free DevNet SOL. So if I open up that address, you can in Solana Explorer, you can see that it has no balance. It's a balance of SOL is accounted does not exist. Data size is 0, etc. So if I go and copy that address and then go to faucet.solana.com, paste in my wallet address, and let's ask for 5 SOL. Why not? And you'll see the message airdrop was successful. If I go back into Solana Explorer, you will see that I now have 5 SOL. Excellent. Great. So let's go and I'll clear those old log messages, and let's hit deploy again back in Solana Playground. Good. So it's deploying, and it says that it can take a while, which it does. And you'll notice while it deploys, it actually takes a little bit of my SOL to do that deployment. And it's finished successfully. So let's go check this out on Solana Explorer. There's actually a transaction for deploying my program. And you can see that transaction was successful. My deployment was successful. Good things. Excellent. So back here, we have our Solana program, and it's been deployed on Solana DevNet at the address. You'll see, by the way, that Solana Playground actually added our program's deployed address inside declare ID, and in Solana Playground, we can actually go and search for that address and find our program there. It has some executable data. It's upgradable. There's the upgrade authority, which is the temporary key that Solana Playground made for us. In my case, it starts with F. Great. Solana Playground also has a test tab. It's this little test tube on the left. And this allows us to actually invoke any of our instruction handlers on the blockchain straight from Solana Playground. So in this case, I can go and set the favorites for the temporary wallet that Solana Playground made for me. I'm going to specify my favorite number, which is 7. Click custom. Color, which is red, custom. And hobbies, which is skiing and bike riding. That looks good. Custom. So as well as our favorite things, people calling this instruction handler will also need to specify the accounts that they want to use. So for the user, pick the current wallet. For the favorites, pick from seed. And the first seed will be what we had before, which is the string of the word favorites. There we go. Oops, sorry, I need to hit that string custom favorites. There we go. I'll add a seed, which is just the current wallet. And that matches what we had before, where we're calculating the seeds to find this favorites account from those inputs, the word favorites and the current user's wallet. Now, our program actually checks that the favorites account we write to belongs to the signer. And I'll show you what happens if someone else tries to write there later on. The program is already written for us. It's just the public key of our actual program. And I think that's it. So we can go, let's make that seed. Click that generate button. And if we hit the test button, we've actually made a transaction to our program. So let's open that up on Solana Explorer. So in Solana Playground, here is our transaction. And it had only one instruction, which is the call to our set favorites. And if you look in the logs here, you can actually see some really interesting things. And I'll make this font a little bit bigger as well so you can see that. It says, greetings from our program's public key. Our user our wallet address, their favorite number is 7, their favorite color is red, and their hobbies are skiing and bike riding. And you can see that that's actually saved that out to that account. The way you can do that, by the way, is you click on favorites. And if you just do fetch all, you can actually see that in Solana Explorer, we have for the public key of our user, we have a number, a color, and a set of hobbies. Now, what happens if another user tries to write to our favorites? So back here, if I pick for user, if I get rid of that and I replace current wallet with random, but I'm going to leave in the favorites account that was made from the previous user. So if I test that now, if I try and run a transaction where I'm writing to someone else's favorites account from a random wallet, you will see that a seeds constraint was violated and the instruction did not complete successfully. This is one of the great things about Anchor, is that these controls over what accounts people are allowed to write to are, really handled for us. Most of it was, this logic that we set up inside the set favorites account struct, where we said that the user is whoever signs the transaction, and the favorites account must be made from these seeds. If they specified a different favorites account that was not made from those seeds, that's why we get a seeds constraint was violated. So you've now made a program, deployed it to Solana DevNet, and seen how Anchor's account constraints allow us to control access to data on the blockchain. You've also, by the way, written data to the blockchain and read it back. In the next steps, we're going to install Solana on your own machine and create more programs that do more useful things. See you soon.